Okay, so in this lesson, we're going to look at simplifying radical expressions. Now, we've been working recently with rational expressions, which are fractions that are written with a polynomial in the numerator and a polynomial in the denominator. Radical expressions are expressions that contain radicals. And to be explicit, this symbol is a radical. So whenever you have this symbol included in an expression, you're dealing with radicals. And we're going to start by talking about a couple of properties. The first property is the product property of radicals, and it's the product property because in this case you can see that A and B are multiplied together, and product is a result of multiplication. Notice that we have a restriction that A times B has to be greater than or equal to 0. That makes sense. We can't have a negative in the under the radical. So once A times A and B are combined, they have to be greater than 0, greater than or equal to 0 combined. The property tells us that if we have inside two factors inside of a radical, we have permission to just separate them into their own radical. So instead of A times B both under the radical, then you can have A under its own times B under its own. And notice the condition still persists. A has to be greater than or equal to 0 because you can't have a negative, and B has to be greater than or equal to 0 because you cannot have a negative. All right, so the other property we'll use is called the quotient property of radicals because it deals with fractions. And it says that if you have a fraction inside the radical, you can separate it into a radical in the numerator and a radical in the denominator. Same condition, A has to be greater than or equal to 0 because you can't have a negative under the radical. But B has its additional constraint that it cannot be equal to 0, and the reason for that is obvious. If you had a 0 in the denominator, you would have an undefined fraction or ratio. So these are something to pay attention to. We don't tend to do the Mayday, Mayday, caution, danger, Will Robinson, and immediately look for what might make B equal 0, but it is something to pay attention to. Okay, so let's do a couple of examples. I think that's the best way to kind of parse through this information. If I have, we're being asked to use the product property of radicals to simplify a radical. So I have example 1, the square root of 32. Now, in this case, what I want to do is I can actually do anything I want. I can use this first property to write, I could write this as the square root of, 2 times the square root of 16, which actually turns out to be the best choice, so let's choose another one. 8 times the square root of 4. All right, that's not a bad choice. I can also write it, well, I've already alluded to the fact, 2 times the square root of 16. The only reason this is the better choice is it gets us to our simplified goal in one step. Notice the square root of 2 is as simple as it can go, but the square root of 16 is 4. So you would have 4 times the root 2. It's customary to write it in this order. Notice I switched to the values. And I skipped a step in here. I think it's intuitive once we've looked at the property, but the step I skipped was to have rewritten this as the square root of 2 times 16, then the square root of 2 times the square root of 16. I'm certainly in class not going to make a big deal about that. If you apply the property correctly, I'm totally fine with you skipping this step right here. But let's take a moment to look at the step I threw out here in the middle where I said it wasn't the best choice, and let's look at what happens there. I'm looking at 32, the square root of 32, and I immediately separated that into factors of 8 times 4. So if I simplify this, I end up with 2 times the square root of 8. Okay, we're good to go there. But we should almost immediately notice that there is a contained 4, a factor of 4 contained in the 8. So this would be simplified to 2 times the square root of 4 times the square root of 2. So 2 times the square root of 4, is 2 times the square root of 2. Wow, that's a lot of 2's. So that would be 4 root 2. And notice I ended up in exactly the same place that I ended up in the beginning. So it doesn't matter if you don't make the best choice first. What matters is that you keep going until you're finished. And with practice, you'll get to where you automatically notice the best choice to use. All right, so let's give a couple examples for you to work with and practice on. All right, there you go. And you should know by now when I say let's find a couple of examples, I always mean more than that. So let's move on. We have example 2. And now we're going to work a little bit with the product rule when I have variables under the radical. Those can simplify using exactly the same properties. So in example 2, I have 9 times x cubed. Now, we can handle these exactly the same way that we handle integers, but it's a little bit trickier in the sense that you have to group these out in a meaningful way while you work. So let's look at doing that. I want to separate this first, just immediately. I want to take the numeric value and the variable value, and I'm just going to separate those out so I can handle them apart from each other. Easy enough for the root 9 is obviously 3, but I'm left with root x cubed. Well, we know from working with radicals over the last few years even that the square root of something squared equals whatever the thing is inside, because if you square something and then take the square root of it, they're inverse operations and you're just left with what's inside. So to process this radical with a variable in it, we want to write it that way. So I'm going to take the 3 along for the ride, and I'm actually going to write this as x squared, and this time I'm going to do the middle step, x squared times x. So we know, remember that x squared times x is the same thing as x to the 2 plus 1, which equals x cubed. So I haven't changed my value, I've just separated the factors out. Now, if I write them under separate houses, by the way, that's a phrase I'll use sometimes. I got it from my favorite YouTube teacher, Patrick JMT. If you separate them into separate houses, you end up with root x. And so that's 3x root x. Okay, so the first separate the numeric value and then the variable value. Reduce the numeric value the same way we've worked in examples 1 through 4, and then reduce the variable value by creating powers that match. Remember, this is a square root, so powers that match the root that you're taking, and then whatever's left over is just left over. Let's do another one of these examples. I think it's an important process, so let's do that again. All right, so let's do, we want to simplify 32m to the 5th, and that's a square root. So first step, obviously, separate my numeric value from my variable value and deal with the numerics first. Well, 32 we already did up here, so I'm not even going to do the steps on it. I'm just going to take my value. Remember, we did 32 here, so we know that it's 4 root 2. And then I want to deal with my variable. So I know that m to the 5th is equal to m to the 2 plus 2 plus 1. And because I know that, I can rewrite this as m squared times root m squared times root m to the first power, which I won't write. So that's the m squared times m to the first power. So now let's reduce it. I have 4 root 2 times m times m times root m. And now let's write it in the proper way. We're going to bring all of our 4mm, which would be 4m squared. And then I'm left with a root 2 and a root m. And it's customary to put those together under the same radical. So what did I just do there? Well, I worked backward from what we've already done. If I have two factors, each independently under a square root, I can put them back together under the same square root. So all I did was I took, in this case, it would have been root 2 times root m, and I put them together under root 2m. All right, so now a couple of examples for you, which is sure to be more than a couple. All right, there you go. So you should definitely pause the video and practice these before moving on to the next part of the lesson. All right, so let's do another example, example 4. And in this case, we're going to take the square root of 13 over 100 and simplify this. Okay, well, we know, remember from our first properties up here, that the quotient property tells us if I have a fraction inside a radical, I can take the numerator and the denominator separately under their own radical. So that means I'm going to rewrite the square root of 13. 13 is prime, so clearly that's not going to simplify or reduce, but the square root of 100 is immediately obvious as 10. So I end up with the square root of 13 over 10. Now it's customary to keep the radical in the numerator, and so we're happy, which makes no sense at this point to you probably, but we're happy to keep that root 13 in the numerator, nothing else to do with it, and then a 10 in the denominator. Let's do another example. This one with a variable. So 7 over x squared, and the entire thing is one radical. First I want to separate the 7 over root x squared, and now handle them separately. Well, square root of 7 is just square root of 7, nothing happens to that. But the square root of x squared, remember, square root, this is a 2 and this is a 2, they're processes that undo each other, and so I'm left just with an x, and that would be the end of the road for that problem. Let me give you two real quick just to practice before we move on to another concept to work with. So number 11, I'll write these out without pausing. 2x cubed times, oh, that's wrong, I don't want to do that, sorry. Number 11, 1 over y squared. And the whole thing is under a radical. And let's do number 12. Let's take the square root of 81 over x cubed. So go ahead and pause and do those real quick and come right back. All right, so a minute ago when I talked about the radical being in the numerator being totally okay, we are going to do something now called rationalize the denominator. Okay, rationalize the denominator. And what that means is it's been historically a no-no to leave a radical in the denominator. So when you finished this problem, you should have ended up with 9 in the numerator over root x times x. And the problem with this problem is that it is pretty much considered bad to keep that radical in the denominator of a number, or of a rational number, and excuse me, of a radical number. So we are going to do a process called rationalize the denominator, which basically gets this radical out of the denominator of a fraction. Now I'll tell you, trends happen in math just like they happen in fashion and music and art. And the trend is more toward not feeling that you have to always rationalize the denominator. Numbers like this are much more acceptable today than they used to be, but it's still a process you need to be able to do. The thought of getting rid of a radical in a denominator, how would you do it? And so we're going to do it by multiplying this fraction by 1. Because if I multiply this number by 1, I haven't changed it in any way. But like always when we're dealing with fractions, we always multiply by an expression of 1 that does what. So what we're going to use for our 1 is we're going to take 9 over x root x, and we're going to multiply root x in the denominator times root x in the numerator. Clearly that equals 1, and the advantage to that is that when I do that, the square root of x times the square root of x equals the square root of x squared. But remember, if you have a square root and a square, then it just reduces itself to x. So the outcome here is 9 times the square root of x over x times x, which would be x squared. Now, that doesn't necessarily look any prettier than the original, but it's customary to get the radical out of the denominator. And so being able to do that is an important step for you, or important process for you to work with. Let me give you a couple problems to practice on that. There you go. Go ahead and pause the video and finish those, and we'll finish up this lesson. All right, so now let's pull all this together with example 6 and 7 and start working with these numbers in expressions, because later we're going to work with them in equations. So let's look at an expression that involves radicals. Suppose I want to add 4 times root 10 plus root 13 minus 9 times root 10. Oh, that's it. So suppose I want to combine these. Well, these think of this as you're working and developing the skill. Think of them in terms of 4x, right? So let's call root 10x plus y, because root 13 is not the same as root 10, so I'd use a different variable, minus 9x. So radicals in this form, or adding and subtracting radicals, is really the same thing as adding and subtracting with variables. You have to have like terms before you can combine them. So with 4x plus y minus 9, you would automatically subtract 9 from 4x to get minus 5x, and the y doesn't combine with anything, and so it stays in the problem. Same thing is true for the radical. You have 4 times root 10 minus 9 times root 10 would equal negative 5 root 10 plus root 13. Do a quick check to see if these reduce in any way. 10 does not reduce. 13, because there's no perfect square contained in 10, and 13 also does not reduce. Okay, so adding radicals and subtracting radicals is really just exactly the same thing as adding and subtracting with variables. But there is a little extra step you have to take, and that has to do with the whole simplifying thing. So let's look. 5 root 3 plus root 48. Okay. Before you can start combining them as like terms, it's a best practice to go ahead and start to reduce these to simplify your radicals. So 5 root 3, square root of 3, can't do anything with that, but 48 certainly has a contained perfect square. So let's write that out. I have 5 root 3, which we know isn't going to change in any way, but 48 is the same thing as the square root of 16 times 3. Well, now I'm looking at 5 root 3 plus the square root of 16, which we can already see is 4, times the square root of 3. Well, if I go ahead and reduce that 4, or the square root of 16 to a 4 root 3. I'm looking at 5 plus 4 is 9 roots 3. Okay, a couple examples for you. All right, so finish those up, these last 3, and come back and we'll do our last part, the last part of the lesson. All right, so now distributions with, oh, I'm running out of paper. It's a good thing we're almost done. Distributions with with radical numbers. So let's go ahead and put example 8 up here. So I have the square root of 5, and I want to multiply this to 4 minus the square root of 20. Holy moly. Okay, well, it's a lot going on, but really all we're doing is distributing a monomial to a binomial. We're using the same process. We're going to rainbow distribute. So if I distribute 4 times the square root of 5, I get 4 root 5 minus root 5 times root 20. And in this case, it's easier just to do root 5 times root 20. Just write it out because I'm going to reduce this root 20. So I have 4 times the square root of 5 minus, well, root 20 has a contained perfect square in it. Yes? Root 20 is the same as the square root of 4 times 5. So if I separate those, the square root of 4 times the square root of 5, I get a 2. So root 20 is really the same thing as 2 times the square root of 5, right? But I still have a square root of 5. So let's track those to make sure. This square root of 5 stays in the problem, but 2 square root of 5 is really the same thing as the square root of 20. So let's clean this up just a little bit. 4 root 5 minus 2, well, the square root of 5 times the square root of 5, square root of 5 times the square root of 5 is the square root of 5 squared. Inverse operations equals 5. So let's take 2 times 5 then is 10. So I'm done. I'm done sooner than I thought. One more example. Let's do a binomial type to a binomial type. They're not actually monomials and binomials, but they're types. So I have the square root of 7 plus the square root of 2. 7 minus 3 root 2. Okay, so if I were going to rainbow this, this would be like having A plus B times, I'm sorry, I've made a mistake here. This is the square root of 7 times the minus 3 times the square root of 2. And if I were to, this would be A plus B. 7 is the same as A, right? Minus, well, this would have to be C because they're not the same thing. Or I could call it 3 times B, actually. Let's do that. So if I rainbow this, I get A squared minus 3AB plus AB plus 3B squared. Okay, so we're used to working with operations that look like this, but now let's do it with a radical. Okay, so I have root 7 times root 7. Well, we already know the square root of 7 times the square root of 7 is the square root of 7 squared, so that's just going to give me a 7. Then the square root of 7 times negative 3 root 2, that's going to be minus 3 root 7 times root 2. Then I'm finished with the first term into the second number. So root 2 times root 7, well, that's going to be plus root 7. I'm going to write it in the same direction here. 2, because remember, multiplication is commutative. It doesn't matter which one I multiply first or which order I take them. Factors multiply to give you the same value. Then the last term would be square roots of 2 times minus 3, so that's going to be minus 3 root 2, and this is going to be squared. So here I have my A, right? I've combined my A squared just becomes 7, minus 3AB, 3 times my A and B, plus my A and B, plus 3 times B squared. So I got the exact same thing, or the exact same pattern playing out here. So let's look at combining some things. Well, 7, and this is actually not a radical because the square root of 2 squared is 2 times 3 is 6, right? So this could actually just be rewritten as negative 6. 7 take away 6 is 1. Cool. Then minus 3 times, let's call this root 14. I'm going to go ahead and write this part out. Plus, remember you can just multiply inside, so that'd be root 14. Okay, and then let's clean it up. 1 minus, well, 3 plus 1. So negative 3 plus 1 is negative 2 root 14s. Look for a combined perfect square, and by that I mean, can I multiply 14 by 4 to get any number? Obviously 1 is a perfect square, but it doesn't do us any good. 4 times nothing gives me 14, so this is as simplified as it can be. Or another way to do it, if you're not sure, is to go ahead and factor. So make a factor tree. 2 times 7 is 14. Nothing is represented twice, so there's not a square in there. Cool, huh? How fun is that? All right, let me give you a couple more examples, and by a couple I probably mean 4. And I might mean 3 only because I don't have room for 4, but let's see, and I'll be right back. All right, so lucky you, there was only room for 3 more. But look at here, I'm going to give you a little hint. These first 2 should be pretty self-explanatory. This one, you can certainly do exactly the same process we did up here, but this one has a little hint. That's a wink. Maybe that's not how you make a wink. That's a wink, right? I'm going to wink. Give you a nose. Okay, that's bad. Anyway, look for a pattern here that you might recognize from before.